All right. What's up, guys? I hope everyone is doing well or kind of well, considering your test is in a couple of days. All right, cool. So I hope you guys looked at it before. I think it was pretty straightforward besides this, right? Besides this, but this isn't too bad once we actually go through it. It's not too bad. All right. So first question, ranking them in order of SN1 reaction, right? So give me 1 second, guys. My bad. Someone was at my door. All right, so for the first question, we're ranking in terms of SN1 reactivity, right? So what do we look for? What's going to be our main focus in terms of identifying the answers for this question? Anyone?
If it's primary, secondary, or tertiary.
Nice. Yeah. So I think that's the best way to go about this. You look at if it's primary, tertiary, secondary, methyl, right? And we know for SN1, the more substituted substrates react the fastest, right? So what is going to be the fastest? Nice. Yeah, third one, right? It's the only tertiary one. Okay. So after this, we have two secondaries, right? So out of these two, what do you guys say? Oh, shit. Oh, yeah, my bad. I was tripping. Yes, yes, yes. These are all secondary. Yeah, these are all secondary. Which one would you expect to be the fastest, though? Yeah, my bad. I was thinking of the leading group as, yeah, okay. So this is the fastest because it has the best leading group, right, out of these three secondary substrates. Now, these two, how would you break the tie? Would we still do leading group or what? Yeah, even if this had the better leaving group, right? This will still be the answer because this is sp2, right? We don't do reactions at sp2 carbons. So based off of that, this is second fastest. And between these two, what's gonna be the faster one? Yeah, Br, right? We don't use reactions at sp2 carbon, so automatically this can be the slowest one that we have. All right, questions about this? Cool. All right, so moving on. All right, so this question states which one is going to undergo E2, or if it doesn't undergo E2, identify it, right? So this one, is it going to undergo E2? So no, even though I got a bunch of yeses. So why is it no? There we go. Yeah. Well, there is a beta carbon, right? But there's no what? There's no beta protons, right? So yeah, just because it has an alkyl halide, just because it has an E2 base, right? That doesn't necessarily mean it's undergo E2. Look at the very basic definition of E2. You need a beta proton to do elimination, right? So here, alpha position, beta position, there's no hydrogens there. Beta positions, no hydrogens there, right? So no E2 because no beta protons, right? So don't rush, right? What about this next one? Okay, yeah, no, because why? Nice. Yeah, so we do have a good leaving group, right? Even I think she mentioned this briefly. This is a good leaving group, but chloride is a very weak base. Remember with E2, we want a strong base, right? So because Cl minus is a weak base. And so why is it a weak base? How can we tell? Yeah, right. So this goes back to chapter 2. It comes from an acid. And in this case, it comes from a strong acid, right? So it's going to be a weak base. All right, what about this one? Yeah, it will. Okay, so someone give me a reason. Yeah. So one thing you should know is if you see this NR2 negative, and R could be anything. R could be a hydrogen, or R could be CH, carbons, right? You see this. This is a really, really, really strong base. Your amides. Amides are really strong bases because amides are really strong bases. And so they prefer E2, okay? And plus, in this case, compared to the first one, remember this is also an amide, right? This is this, right? In this case, also there are beta protons. Okay. So make sure you know this. This is a really strong base. All right. Questions about this? Cool. All right. Let's move on. Ranking carbocation stability. So one is the most stable. Okay. Most. Okay. Yeah. What is the most stable? Yeah. Nice. Yeah, the middle one. Right. So same thing here. You look at the more subbed carbocation. In this case, tertiary. So it's the most stable. Out of these two, both these are, excuse me, both these are secondary. So what do we do here? Right is 2. Okay, right is 2. This is 3. So how did we come to that conclusion? First is SP. Yeah, so this is sp2 hybridized, and this is sp. But remember that what stabilizes carbocations? What was that word? Hyperconjugation, right? Hyperconjugation. And so hyperconjugation is you have donation of electron density from sp3 carbons, right? So if we look here, we have 2 carbons being able to hyperconjugate because both of these are sp3, right? Here, how many carbons are able to hyperconjugate to stabilize that carbocation. Yeah, only one, right? Only this guy right here. That's the only sp3. This is sp2, so by definition, it cannot hyperconjugate. Okay. Questions about this? Ring strain would be a factor here. No, there's very minimal ring strain in cyclopentenes. Usually you see ring strain in squares and triangles. Awesome. All right, so next question, right? Which one of these is undergo E2 the fastest? So what do you do here? What are we looking for? Right. So we need the chair to have an axial leaving group, okay? And so once we do that on both these chairs, then we could just fill in everything else that's a relative. We figure out which one of those chairs is the lowest energy conformer, right? So here on this cyclohexane, this is on a wedge, right? And so what does wedge mean on a chair?
Up.
Yeah, wedge means up, right? And so we need our leaving group to be axial. And in this case, we need to be axial up. So what you do is you just, on this chair, find an axial up position, okay? This is an axial up position. So what I'm gonna do, I'm gonna put my bromine right here, okay? Once we do that, everything else is pretty simple. We just put everything else on, right? So right here, that's where the methyl is gonna go. And is it gonna go, how's it gonna go? Give me both those words, yeah. So equatorial, down, right? So this is a dash, it's gonna be down. This is an equatorial down position. And then right here, that's where the isopropyl is gonna go. So once again, how's it gonna go on here? Yeah, same thing here, right? Equatorial down. Okay, so we got that, right? Same thing here, right? Bromine's in the same spot, same orientation, so we could just make it easy on ourselves. In this case, the methyl is on a wedge, so it's up. So that means here it's going to be axial up. Same thing with the isopropyl, right? Which one of these conformers is lower in energy? Top or bottom? Yeah, it's the top, right? So this goes back to what you learned previously. The one with, well, in this case, the one with the largest group in the equatorial position. Largest group in the equatorial position is isopropyl, right? And plus, in this case, you have both the alkyl groups in equatorial. So that's even more of a stabilizing effect. Since it's the lowest energy conformer, it'll react faster, right? Because you have a lower EA. Okay, so that's all you do. You put the leaving group on there in the axial position, and then put everything else on there. Identify the lowest energy conformer. That's going to react faster via E2, right? Questions? Cool. All right. Next one. So we got to identify first what reaction pathway it's going, right? You have 4 options: SN1, SN2, U1, E2. We're going from a chlorine to an oxygen, so we know it's either SN1 or SN2, right? So how do we break the tie? Okay, we could look at the nucleophile. Is the nucleophile weak or strong? No, right? Nucleophile is weak because it's not charged. Your neutral nucleophiles are automatically weak. Okay, so since this is weak, it's automatically what? Is it SN2 or SN1? Yeah, SN1, right? So it's SN1. Now, I think it's best if you do the actual mechanism because that'll tell you how many humps your energy diagram is going to have, right? So the first step would be what? Yeah, chlorine leaves. I'll draw it up here. And so you have a carbocation, right? What is the next step? Yeah, so here your nucleophile attacks. And then what is the last step? Yeah, we depronate, right? Because we can't leave it in a charged state. So here, like I said, anything could come in and take that proton. It could be another ethanol, it could be chlorine, right? You form that, okay? So we have 1, 2, 3 yield arrows, right? So that means we have 3 humps, okay? We have 3 humps on our diagram. Something else we have to figure out is it negative delta G or is it positive delta G, right? So what do you guys say? Negative, okay. Someone tell me a reason why you guys said it's negative. Nice. Yeah, so we're going from a CCO bond to a CO bond, right? So we know, let me go over here. CCO to CO, right? And so since CO is bigger, the bond is going to be longer, right? Longer, therefore it's weaker. Whereas here, we know oxygen is smaller than chlorine, so shorter bond, and therefore it's stronger, right? And so since we're going to a stronger bond, we're going to a more stable energy state. So negative delta G, right? So now we just figured out how to draw our energy diagram, okay? So let me draw it real quick. Right. So like that, 1, 2, 3. So the first hump should be your highest, right? Because this first step is your RDS step, so it's the slowest. You're gonna come down, you form a carbocation, nucleophilic attack, right? And you form this point right here is the formation of this, right? And then you have an acid-base reaction. Which one for yeah, I was trying to look at that. Let's do this one. It's going to be a little bit higher in energy because you have a positive charge on oxygen, right? So I think here, I think I made it a little bit higher. Not that you could tell, but on the key, I'll make it a little bit. Let me just redraw it, honestly. All right, so we're gonna go to the first hump, right, which is the highest. We're gonna come down, second hump, and like that, right? That would be my assumption. So we're comparing the carbocation to the positively charged oxygen atom. Since oxygen is electronegative, it won't be able to bear that positive charge as well as the carbon. So it's a little bit higher energy. Cool. So we got that, right? So we know this is E for energy. So depronation step is actually exothermic just by the bond being broken. Yes, because depronation steps, they occur, your acid base steps within a given mechanism are going to be your fastest steps. They occur very readily and they are very favorable. So that's why this portion right here is exothermic, highly exothermic. Yeah. Cool. All right, so everything else we have. So let me just do this. This is your negative delta G, right? And then this portion right here is your EA. I'll just put EA. Okay. I know it's ugly, but all right. So now we're going to answer these other questions. So if we change the nucleophile to sodium iodide, right, and the solvent stays the same, right, what would happen? It's the rates. Cool. Would the third TS also be the lowest in E? Yes, it would be. Yeah, so this peak right here is going to be the lowest because, so the first step, so let me go through this then. So the first step, right, this is where chlorine is leaving. This is where you're forming the carbocation. So it's going to be the highest, right? You're going to come down, you're going to form the carbocation, right? You're going to come down and form the carbocation. Then up here is where you have the actual attack happening with ethanol, okay? The attack happening is going to occur a lot faster than Cl leaving. That's why it's a little bit lower. You're going to come down over here. This is where you form this species right here, this positively charged oxygen thing, right? This is that. Then you're going to go up a little bit, and this is where depronation happens. And so, like I said, acid-base reactions, they occur very, very fast. They're a lot faster than just regular Lewis acid-base reactions like what we have within these first few steps. And so that's why it has the lowest EA, pseudo to EA, right? So yes, the third transition state is going to be the smallest. Cool. Okay, I'm going to assume yes. Increase, better love. So no, Owen, we're teaching nucleophile. Yeah. Yeah. Okay, so it is a better nucleophile, but if the solvent stays the same, right? If the solvent stays the same, so we have ethanol, right, as the solvent, and then now we change it to, or not the solvent stays the same, and then now we change the nucleophile to, let me see, I draw it out. So we have I minus, right? And we have ethanol. Yeah. So in this case, even though it is SN1, we're going to assume that it still proceeds via SN1. Since this is charged, it's going to get caged by this, right? And so even though it is technically a better nucleophile, you have to remember the context. We're in a polar we're in a polar protic solvent. So since this is charged, it's going to get caged, right? So the rate decreases. In our previous example here is just ethanol, right? So there's no caging happening because there's no other thing in the solution. It's just this and it's just ethanol. So there's really nothing hindering anything else, if that makes sense. The solvent doesn't, so if it's salicylic, right? So in this case, it is salicylic, where the nucleophile is a solvent. It could be above or below, doesn't matter. Yeah. Oh, I forgot to do the rate law. What's the rate law? Yeah. So in this case, since it's SN1, it would just be the alkyl halide, right? So RX. Okay. Cool. Everyone understand this first part? I know it was a little difficult question. Right? Everyone good? Good-ish. All right. Let's see. Yes. What happens to the rate if the alkyl halide was changed to 2-bromo 2-methyl cyclopropane? Wouldn't work faster because tertiary X into secondary X. Yes, Charlene, yes. So we have actually two good things happening here, right? So we have, what is it, propane, right? So we have it going to a tertiary, so that's good. What else is good? Yeah, better leaving group, right? So we have two things happening. So faster because tertiary and better leaving group, right? Cool. And then last one, what happens to the rate if the alkyl halide was doubled? The concentration of the alkyl halide was doubled. Yeah, rate doubles, right? Because it's part of the rate law, which we put right here. Okay. Questions?
She probably wouldn't ask this, but if it was like a better leaving group but a worse, like
Okay.
would it
Yeah.
would one matter over the other? Like would
Yes.
take preference?
Yeah. So she would. Yeah, you're right. She would never ask that, just because that's a very difficult thing to do. Like where you're increasing something and decreasing something else, so you have like conflicting variables, right? She'll never ask that. She'll only ask a question where you change just you're changing just one variable. And even if you change two variables, those two variables are going to change in the same manner, if that makes sense, right? Here we changed two variables, but both those variables increase the rate. Cool. Okay. All right. So next one, mechanisms, right? So you guys tell me what mechanism, what pathway is this going to go through? Not SN2. Yeah, it's E2 only, right? Remember what I said up here. If you have this, a negatively charged nitrogen atom, automatically E2, because these are such strong bases that they will do E2 over anything. Okay. Since they're really strong bases, they're not want to substitute. They're not going to want to substitute. They're going to want to grab a proton. So it goes through elimination. Does that make sense?
Yeah. Hey, Jeet.
Yes.
So I don't know if I'm the one who's kind of messing up in the chain here, but looking at the book mentions that same thing where if it's a really strong base, it's going to be E2.
Right.
But Doherty gave us this likely mechanism guide, which sort of, I guess, drew a finer line between if it's strong bases and, in the case of a secondary electrophile, if it's a strong base and unhindered,
Right.
then she could, in this table she put out, it's like SN2/E2. And I know that they don't happen at the same time,
Right.
but I guess it seemed a little bit a conflict with regards to this, how this edge case gets handled.
Okay. So let me do this. Let me, all right, give me a sec. I'm gonna pull up the thing and I'll show you where to exactly look. If Blackboard loads. Handouts. All right. So let me pull up the chat real quick. All right. Yeah, so we had a secondary, right? We had a secondary and we had well, we had secondary, we had strong base, unhindered, right? Or
Yeah.
relatively unhindered, because what was it? It was,
You just like you just had a hydrogen and an ethyl.
yeah. So it's relatively unhindered, right? Because of the ethyl group, but still, let's say it is unhindered, right? If we go down here, strong base unhindered, right? So I think she clarified it that anything with NR2 minus, it's mostly E2. And so
Okay,
this
so
is,
that's how we
yeah,
handle that.
yeah. So this is the case for just hydrogens, right? Mostly E2. But what happens if we put on an ethyl? Now it's even more E2. Does that make sense?
Because it's an even stronger base.
It's even stronger base, and plus it's even more hindered now.
Okay.
Cool?
So if it was anything besides that amide, it would be both, but because it's NH2, it would just
On
be
it. Oh my gosh. Okay. Okay, so let's do this. I know this chart is a little weird, but anything that is this, E2. Because I've never seen this, or I've never seen this do SN2 ever on any of our exams. Okay, are we good?
Okay, I'll take it.
Okay. Yeah. Awesome. Because
Because this seems
there's,
to be a bit of an edge case that gets tested quite a bit with these secondary
yeah,
alpha carbons. And I'm like,
exactly.
oh, is it hindered, unhindered? And I'm like, I've seen the stuff for hindered. I think she spoke about there being 4 carbons or more.
Right.
And, having this one it's like, yeah.
It gets a little convoluted. I just remember that anything with a negative charge on nitrogen, super, super strong base. So it's going to do E2, regardless of whatever it has on it, right? If it's something else like hydroxide or an alkoxide, then you'll get some SN2 because negatively charged oxygens aren't as strong of a base as negatively charged nitrogens, right? Does that make sense? So I guess that's where you draw that line. Doesn't matter if it's an amine or amide. Yeah, so if it's an amide, so in this case it's an amide, right? E2 all the way, only E2, right? If it's an amine, then you'll have SN2. So if you have like N, oh my God, and R3 SN2. Cool. Does that make sense? This is the only exception where a neutral nucleophile is considered a strong nucleophile. This right here, an amine. Okay. I probably just made things worse, but it's fine. Okay, so are we good on this, that it's E2? Right, negatively charged nitrogen atoms, always E2. Okay, except, I forgot the exception, except for this. This would not fall under what I just said. This would be a weak base. And this is on our chart, right? This is a weak base. Anything else that has a negatively charged nitrogen, super strong base, E2, because it resonates. Yes, because it resonates. You draw the Lewis structure, it will resonate. And plus this thing comes from an actual acid. HN3 is an acid. I forgot the name, but you guys can Google that. Right? It comes from an actual acid. That's why it's a weak base. Okay. Are we good? Hydroazoic. Oh, hydroazoic acid. Cool. All right. So it's E2, right? And so it's concerted, right? The mechanism concerted. And so we have two beta positions. So we have this, we have this, right? I'm just put B just so I don't want to draw everything. So it's concerted, so everything happens at the same time. So grabs a proton, these electrons move right here, kicks off Br, right? You do the same thing for this proton. So I'm not going to do that. So you get a pi bond. You get a pi bond right here, right? For the one I just took off. And you get a pi bond at the end for the other one. Okay, so that's it. No SN2 product because amides are very, very strong bases. They're not good nucleophiles because they're super strong bases. All right, next one. What's happening here? Okay, yeah, so here it's E2 and SN2. Okay, and so why is that, right? I hope you guys have this in front of you. I'm gonna go back to the chart and prove it to you guys. So what do we have? We have a secondary, right? So secondary, and it was, I think it was methoxide, right? It was methoxide. So out of this entire row, what would it fall under? Poor nucleophile, weakly basic, good nucleophile, which of these? Yeah, so it's not poor nucleophile because of the charge, right? It's not hindered because there's just a methyl on there, right? And so now it's between these two. The strong nucleophile, but now you can determine, is it a strong base or is it a weak base? Does this come from an acid? So its conjugate acid is methanol. Do we call this an acid? We do not, right? It's called methanol. Since it does not come from an acid, this is a strong base. Okay, right here, strong base. RO negative, RO negative, small straight chain, methyl ethyl propyl, right? So it's gonna fall in this category. Since it was secondary, SN2E2. Okay. So SN2E2, right? So SN2 product is going to be backside attack. And then you invert the chiral center. Right? So that's the SN2 product. E2 product is what we just did before, right? So we have two beta positions. Let me change this. We have two beta positions, hydrogen here, hydrogen here. And both of these are different, so therefore two different products, right? And then same arrow pushing. Grabs the proton, these fall back. Br leaves, right? So we have this, right? And then we have, after it grabs that one, we have this, okay? And yes, the second one is the major. And then here, this one is major.
Can you explain how to find the major again? It's like both substituted or something?
Yeah, so the major and minor, that's going to be between alkenes, right? So here, we have two alkenes, right? So you look on both these carbons contributing to the double bond formation, right? So here, we have one thing coming off of it. Here, we have one thing coming off of it. So in total, we have two, right? Here, how many alkyl groups are coming off this double bond?
One?
Yeah, just one, right? So if you look on this side, it's just hydrogen. So those are not alkyl groups. Look on this side, just one. So this is disubbed. This is monosubbed. So the more substituted alkene is the major because it's more stable. Okay. If we do the same thing here, what substitution is this going to be? Mono, tri, di, tetra.
Mono?
Yeah, mono, and then this is di, right? So since this is more sub, it's the major. Okay, cool?
Yes, thank you.
Yeah. All right, last one. You guys tell me. Yeah, that's the one you want, right? Because why? Because we have secondary, right? And we have a poor nucleophile. So if we go back to the chart, secondary, poor nucleophile, right here, that's the only one. That's the one you want, right? First of all, so this is usually, yeah, but I'm not gonna give you a definite answer because, yeah, no, I don't. I'm gonna say, okay, Dory says so, then yes. I don't like giving definite answers because a lot of stuff changes. But if Professor Doherty said yes, then yes. Yes, it is. That's the one you win. All right, so that's the one E1, right? So let's do that's the one product first. Leading group leaves, right? And then you have a positive charge. What happens next? Yeah, nucleophile attack. And then you have this, right? And then last step. Yeah, depronation. I think it was, yeah, so I'll use chlorine. And that is your SN1 product. Is this product racemic? Yeah, it is. It is racemic. I'll put R for racemic, right? Because this is a chiral center. Okay, and so since this is a chiral center, both the dash and the wedge would be different RNS configurations. Okay, so that's your SN1 product. And so as far as your E1, so same first step, right? So I'm gonna erase all this. Same first step, but now we look for the beta positions. Here we have 2, right? So here we have this proton, this proton, right? So ethanol is going to come in and grab it. These fall back into here, okay? You do the same exact thing for this, okay? So I'm going to show that. So you have this guy, right? And then if you went up after the one at the end, you would have this. Which one is the major out of the top, bottom?
Bottom.
Yep, bottom, right? Because more subbed. Okay. Questions about this? All right. So what I suggest, if you're still having trouble identifying what pathway it's going to go through, what I suggest is go through these problems, right? Redo these worksheets, redo whatever Professor Doherty gave you in class, redo Mariah's. Let's do this for like an hour or two. Work through these with this sheet. Okay, if you come across a reaction, identify what pathway it goes through using this sheet. Let's do for like 2 hours. Okay. After that, do it without the sheet. See if you've caught some pattern. Okay. That's what I did whenever I started this unit. It definitely helped. I think with the sheet, you'll definitely catch some patterns, some repetitive patterns, right? And so I did that for about 2 hours, 2-3 hours with the sheet, and then after that, I tried it without the sheet. Obviously, I made some mistakes, right? But that's how you learn, okay? So I hope that helps, that strategy. If it doesn't, I'm sorry. All right, so the last one, we're just identifying the products, okay? So once again, what pathway is this going to go through? Yeah, the same one that we did before, right? So when it's a secondary, and we have a poor nucleophile. That's the one you want, okay? All right, so let me draw. So substitution product is going to have what functional group? Yeah, an OH, right? And this is racemic. Elimination products, there's going to be 2 because we have 2 different sites. We have this guy, and then we have this guy. Which was the major, top or bottom? Yeah. Yeah, Katie, there is a depronation. Yeah. But in this case, I just drew the products because that's what I was asking for. Cool. Yeah. So if I'll just say it, right. Leaving group leaves, right. It's actually the same mechanism as this. but instead it's water up here. So you do the same exact thing, except replace this with water. Cool? All right, so this next one, what do you guys say? Not SN2.
I said SN1 because the N3 minus that you talked about earlier.
Okay, so I talked about it earlier. So what did you get from that? How did you come to that conclusion from what I said?
That it's weak. It's a weak
Okay.
nucleophile.
No, so it's a weak base.
Weak base.
Yeah, it's a weak base, but it's a good nucleophile, right? Right. So let's go back here, right? So was it secondary? I want to go back.
Yes, it was.
Okay, so it's secondary, and then we have weakly basic good nucleophile, right? It's one of your examples. We go down, we're in this box. The solvent. What was the solvent? Was it aprotic or protic?
It was protic.
Yeah, it was protic, right? Because it had a hydrogen bond. So SO1E1. Yeah. So yeah, make sure you're able to recognize solvents that are not on that list. Okay. She's not going to give you a solvent in terms of like a solvent name that's not on the list. She'll give you a structure of it. Okay. Here, this is not one of them on your list. So she won't give you the name of this because you don't know the structure of it because it's not on the list, but she'll give you the structure. Does that make sense? So if she gives you the structure of some solvents, you have to know if it's hydrogen bonding or if it's not hydrogen bonding. Mixed up purity. Okay, cool. Yeah, so right here, that's your H bonding site. So SO1E1, right? So same thing as before. Okay. So we have SO1 product. Is this racemic? It is, right? Because it's a chiral center. And as far as the E1 product, you have one right here, you have one right here, two different ones. So two different E1 products. So we have this guy. Do we use beta H on the dashed CH3? So you're talking about this one? No. So this would not be a beta position, right? This would be oh, yeah. So here, this one, you would use this. Yeah. Okay. Right. Whoa. Right. What's wrong with this? Yeah. So no dash, right? And I'm pretty sure she's told you guys this. She's gonna put like wrong answers that she's seen before. So that will be an answer. So make sure you guys are aware of that. No dash. Stereochem is lost because this is sp2 hybridized. Okay. Which one of these is the major elimination product? Yeah. Right. Because it's tri sub. Okay. Cool. Questions about this entire page? Because it's basically the same thing.
I have a quick one for the
Yeah.
last one. I just
Yes.
wanted to make sure for Zaitsev's rule, the one exception was for regional selectivity was for, you said cyclohexanes for E2 only, right?
Right. Yes.
Okay, nothing
Yeah,
else.
that's a good question. Okay.
Cool.
So let me do that then. Okay. So usually your major product for elimination, right? Usually your major product for elimination is the more substituted product, okay? But in one particular case, that won't be true, okay? So say I give you, or she gives you, say she gives you this, right? And she tells you it's going to react with LDA. What pathway is it going to go through?
E2.
Yeah, E2, right? Pretend that's an E. So we have two beta protons here, right? So we have one on a wedge over here, and we have two over here. God, that's ugly. Right? So if we go after both of these, right? Let's just assume we can go after both of these. So this will be the product if I went after this one, okay? The other product is this one. So say she gives you something like this, and she's like, okay, what is a major product? What would you say? Right, the bottom, okay? And so this is where there's a conflicting concept or whatever, right? For cyclohexanes, and cyclohexanes, let me do this. Can't type anymore. Bruh. Let me just go to a new page. Okay, cyclohexanes. Let me do this. E2 cyclohexanes. Right, E2 is cyclohexanes. The only beta H that is going to be eliminated is the one that is trans to the LG. Okay, make sure you know this rule. Okay, make sure you know this rule. So if I go back, I hope everyone got this down. If I go back to the other sheets, the only beta hydrogen that I can eliminate in this question is this one. So what does that mean? This is the only product that is capable of forming. This will not form. Because why? Because this is not trans to the leaving group. Okay, so this is where Zaitsev rule would not apply. So make sure you're aware of that. Questions? Awesome, right. All right, so filling in the missing reagents. What's gonna happen here? What, or someone just tell me what to put. Yeah, so it's gonna be SN2, right? Because you have an inversion. KN3. So not KN3, right? Because we don't have N3 here. CCl, so not CCl, okay, KCl, yeah, that works. Yeah, KCl, NaCl, right? Because in this case, remember, this is your nucleophile, right? So it's chloride, and then something with the metal, right? So it's chloride with the metal. And so we would need to include a solvent because it wouldn't make a difference. What type of solvent? Yeah, right, we need aprotic solvents because it's SN2, right? So DMSO is a good aprotic solvent. What about this one? If it's one of the products. So keep in mind, there's other products. There we go, that's a good one. Yeah. Right, so remember this would do SN1 and E1. So you'll get the substitution products, you also get elimination products, right? So that's a good one. So you could do SN1E1, or you could do, or you could have done, what's something else you could have done?
That last ring with the nitrogens and the hydrogen.
The last ring. Wait, what do you?
Yeah, in the previous question, the one that we kept messing up, forget what it's called.
Oh, this. Yeah.
Yeah.
Yeah, you could have done. Yeah, you could have done this, right? So basically, anything that gives you SN1 and E1. You could have also done something that gives you SN2 and E2. Yeah. So like Jenny said, NaOH. NaOH. Let's do DMSO. Good God. DMSO, right? NaOH, strong base, strong nucleophile. This will give you SN2 and E2. Right. So there's a lot of possibilities. Okay.
Oh, I have a question about this. So, looking at the product, where you have this cis product,
Right.
should we? I mean, were we supposed to read anything into that? As in, like, because I was looking at this and thinking, oh crap, does this mean that, for example, like E2 can't take place or something? I don't know. I was just trying to. I was wondering if I should read anything into this versus trans.
That's a very good point. Yeah. No. I didn't even realize that.
Because seeing that plus the statement one of the products made me think
Right.
SN1, E1 must be the only right answer, or
Yeah.
reagents and shit that deals with that.
Right. No, yeah, that's a good point. I totally missed that. Yeah, so this, since this is cis, right? Since this is cis, E2, if we undergo an E2 reaction, it's going to form a trans product. It will not form a cis product. And so the only possibility is SN1 and E1. I hope she mentioned that, right? She mentioned E2 makes trans only, or does she not? I'm pretty sure, because I didn't.
She mentioned for the purpose of this class, like trans would be the only product that's generally formed, but she didn't say anything about E2 only forming trans
No,
products at all.
I don't know if I'm thinking from when I took Ochem 1 or. All right, let's just do this. Let's just do SN1E1 here. Okay, let's not do E2. Yeah, because if she didn't mention it, then I don't want to make that assumption. All right. Questions about this? I think the easiest way you could have done this is the SN1E1 route, because it is one of the products. I mean, this is one of the products, so you can assume there's other stuff there. And I think the most prevalent pathway that has multiple products, including elimination, is the SN1E1 route. And so I think doing Savolysis or doing something like this would have been the best option. Okay. And then again, she'll have there'll be multiple choice. So at least given that, you could go through each option and think about it. Okay. Awesome. All right. So the roadmap, like I said, I'm not sure how she's gonna do this. I'm assuming it won't be like 6 boxes like she usually does. It'll probably be like 2. Okay. And yes, there is going to be NMR, right? There is going to be NMR because that's how you do the roadmap. Okay, so how would you do this question, right? You have to figure out these missing structures, and she'll give you an NMR spectrum for one of the boxes. So in this case, she gave you the NMR for box A, right? So you figure out that structure, and then you figure out everything else based off like working backwards. Okay, so the formula is this, right? So let's go through our NMR things. So what is degree of unsaturation going to be? Yeah, so it's 4, right? So we know if it's 4, it's going to be we have a benzene ring, right? What else, right? So we have to figure out what the substitution pattern on this ring is. If we go to the benzene region, 6 to 8, you see this, 4H2 doublets. What does that tell you? Is it mono? Is it para, meta, ortho? Yeah, so it's para, right? Para is going to give you the 2 doublets. So we have something like this going on. Now we can start construction of structure, right? So we have A, B, C, D. Something that should stick out to you is this. What is that? Yeah, that's an OH, right? So we know we have an OH somewhere. So now 3H doublet, right? So we have, it's a methyl. And it's connected to what? What is it connected to? A CH, right? Because it's a doublet. So its neighbor is going to be a CH. So if we go to our NMR, well, this is the only CH we have. It's a quartet, 3 neighbors, right? So it's done, right? So we took care of both of these. Now, how many bonds? So it's missing 2 more bonds, right? Notice how it's the furthest downfield. So what do you think it's going to have on it? Yeah, so an OH, right? And in this case, it's also going to have the ring because why? Because that's the best way to construct this structure. Okay, there's no other possibility. This is also going to be attached to the ring. And that makes sense because on the other side, we have a 3H singlet. We have a methyl that's a singlet, and it's a little bit downfield than a normal methyl shows up. So we know this is also attached to the ring. So we have this as our structure, right? I hope everyone got that. Any questions on how I constructed this? Cool, all right. All right, so if we work backwards, right? This thing is going to react with water, and we're going to make this. Okay. Look at the formulas. We're going from some alkyl halide to an alcohol. So what reaction is taking place that you know of? Is it a substitution reaction or is it an elimination reaction? Yeah, so in this case, it is SN1, right? So it's a substitution reaction because we're going from an alkyl halide to an alcohol. So I think it's pretty obvious on what it's going to be, right? So what you do is you would just erase this and put the halide. In this case, it's I, right? Now we work backwards from here. What is going to go here?
CL.
Yeah, same thing, right? Same thing, but CL, because in the mass spec data, you have a 3-to-1 ratio. That's going to be CL, okay? If we go this way, what's going to be here? Yeah, right, so it's going to go E2 because of GBN. GBN is one of your E2 bases. And so the only beta position that has a proton on it is what? It's this side, right? We don't have a beta proton here. This carbon is full. Okay, so you have this. Okay. If we go this way, right, this is going to go through what pathway? Yeah, so this is SN1E1, right? But then you have to figure out, well, what does she want? Bro, what? If your mic's on, could you please turn it off? Thank you. All right, so if this is going to go through SN1E1, right? But then you got to figure out which one does she want. If you look here, the oxygen is there, right? So it's going to go through SN1. If it was E1, it would just be carbons and hydrogens, right? So make sure you use like the formulas and the reactions as hints. Okay, so you have O methyl, right? So you get this ether. Questions? All right, so that's it. All right, hope you guys do well. Hope you guys do well on Monday and Tuesday. Like I said, if you have any questions, feel free to email me. All right, have a good weekend.
Thank you.